in Bangladesh. Everybody is waiting for his lecture. I understand that. So it is a great honor that we have with us Professor Zahid Hasan, and he will be talking on the very special topic that he has been contributing for a very long time, topological quantum matter. And I hope that all the students, researchers, they will enjoy this lecture and they will get benefit from this. So I welcome Professor Zahid Hasan.
Thank you. Thank you for giving me the opportunity to present my results in this meeting. It's wonderful to get in touch. So I'll talk about topological quantum matter. I'll start out giving a very brief introduction. What is topological quantum matter? There are many ways of looking at it, of course. So one way to look at it from a broad perspective is it's a quantum organization of matter where you could realize many quantum field theory objects, particles like Dirac Fermion, Weyl Fermion, or Majorana Fermion, and more. So what is interesting about condensed matter, topological quantum matter, is that you can realize things that you can imagine or conceptually imagine in quantum field theory. Not only that, you can do things beyond that, including things that are, say, Lorentz violating thing. In quantum field theory, you don't violate Lorentz invariance. So this is what is exciting from a physicist point of view. There is also an exciting thing from application point of view or engineering point of view. It looks like in last few years, it's becoming clear that topological quantum matter would be the next basis for next generation quantum computing. So the present generation of quantum computing is not fault tolerant, so you have to implement error correction algorithms and all that. But topological quantum matter, if you can make a qubit out of it, by nature it would be fault tolerant. So there is both physics excitement and potential application. Application is probably far off, I would say probably 20, 30 years. But you need new physics to develop new technology, right? So that's kind of the broader perspective why there is so much interest in this topic. Okay, so in this talk, I'll give a few examples, and both conceptual and experimental, how we are beginning to realize these things. Okay, so let me start out acknowledging my students and collaborators who are on the ground doing much of the work. So much of the stuff I'll be presenting here is collective effort of many individuals, many scientists. I will mention a few: Ilya Belopolsky, Suyang Zhu, Jiaxinin, Goqing Chen, Sonia Zhang, and Guang Bian. They are the key people leading the projects on the ground. Some of them have left they're my students. They left the group. Especially, I'll heavily mention on Suyang Zhu's work. He's now a faculty professor at Harvard. He's no longer in my group. Similarly, Sonia is now at Columbia, and other people have also left the group. Okay, so it involves collaboration with many groups, but it's led by our group in most cases. Okay, so this is the broader theme since this is a physics conference, not just condensed matter physics, so I decided to inject this slide that for decades we have been thinking, physicists have been thinking, it's the broken symmetry that is describing all the fundamental forces or phases of matter, right? So when some symmetry is broken in early universe, the fundamental forces become distinct, electroweak symmetry breaking, or even earlier strong and electro. So all these things are related to some spontaneously broken symmetry, and associated with broken symmetry, there are emergent particles, emergent even in a fundamental sense. So that's a description not only of early universe. It's also, these ideas actually historically developed from condensed matter physics. Like solid has less symmetry than gas or liquid. So it's the breaking of symmetry, or the symmetric consideration, that defines a phase or matter. That's a unifying theme in all over physics. So I would say last 1 or 2 decades, physicists are beginning to realize symmetry is not the only story. There are distinct phases of matter. They may have the same symmetry, but there may be some topological distinction. So the topological classification of forces and phases of matter is now, in last 2 decades, have become a major theme. I would say at least 3 or 4 Nobel Prize, it depends how you count, Nobel Prizes have been given that sort of directly or indirectly highlight this new emergent idea. So I will give examples of topological phases that are kind of like test bed for QFT, quantum field theories, and they're described by some form of field theories. Okay, so let me now give a condensed matter perspective. So in condensed matter, even 10 years ago, when I used to teach condensed matter physics at Princeton, I used to tell students that the condensed phases of matter, electronic matter, are metals, insulators, superconductors, or magnets of various forms. But then just in last 10 years or so, we have seen that this is not the full story. So all these phases of matter, electronic phases of matter, clearly has a topological variance, a topological version, which is neither exactly metal. For example, in insulator, it's neither exactly metal nor exactly insulator. There is a topological distinction, and it's a distinct phase of matter than what we used to teach. So what seems to be happening is now we are in the process of rewriting condensed matter textbook, that there are new phases of matter. So I'll describe some of the new phases of matter that we have discovered in our experiments. The first example would be topological insulator. A conventional insulator is insulating in the bulk and insulating in the surface, or it can be made insulating in the surface. Accidentally, sometimes it can be metallic on the conducting on the surface. But a topological insulator is something, it's insulating in the bulk, but there is no way of making it insulating on the surface. And then the bulk insulation and surface conduction are actually distinct. In other words, surface conduction is always through a helical Dirac Fermion. So it's not through a regular electron. So one way of tracing topology is to go back to quantum Hall effect, discovered in 1980s. In the quantum Hall effect case, you apply a magnetic field in a 2D electron system, and then you see that the bulk has a gap. So bulk is insulating, and the edge boundary has a conducting channel. So the skipping orbit scenario. So then the conduction is quantized. So this quantum is a topologic. This quantum of the quantum Hall effect, this n here, is a topological quantum number. It's not a conventional quantum number, and and then this is a counter of the edge state. And about 10-15 years ago, it was realized if you take 2 copies of Haldane model in the presence of spin orbit, you could create a quantum Hall-like effect without magnetic field, just through the spin orbit interaction. So this is the quantum spin Hall effect. So in this case, the spin up edge electron will move one way, the spin down will move the other way. So now you see that if you do that in the energy momentum space, if you draw the dispersion relation of these electrons, in the quantum Hall case, you have a chiral edge state. You have one channel, one branch. So now by making it time reversal invariant, then you have two branches, right? So this is how these two branches meet at a Dirac point. This is how Dirac Fermion appeared in the system. Dirac Fermion is not necessary for topology in general, of course, because quantum Hall state is already topological. It looked like my screen disappeared. Yeah, is it visible to everyone?
Yes, it is visible. Yes.
Okay, sorry. Okay, so now this helical edge state pair is now described by the Dirac equation. So now you can take this 2D system and its topology is described by one topological invariant, just like the quantum Hall, but a new invariant or different invariant. Now, it turns out there was even more surprise when you consider, what if you consider a 3D crystal? The 3D in the 3D crystal case, it looks like you can stack the quantum Hall or quantum spin Hall state, but then that does not guarantee that all surfaces will have Dirac Fermion. So it turns out there is a distinct new topological state of matter in 3D, which is not a simple generalization of stacking generalization of 2D. How do we know that? Because in 3D, that distinct state is described by 4 invariant, not 1, 2, or 3. So in other words, this state has no 2D analog. So this is why this is the first time this state was called quantum spin Hall effect. This is quantum Hall effect. So now this state, this new 3D state is not, it doesn't show any obvious Hall effect. So that is the reason this term was coined, topological insulator, because it doesn't fall into any of the Hall effects. So this is a totally new state of matter, topologically distinct. So in this state of matter, every surface has a helical Dirac Fermion, and it's not about accident of chemistry, surface chemistry that creates the Dirac Fermion. It's the topology of the electronic wave function. So how do we know that? We know that by chopping and cutting open any surface, it will always have odd number of helical Dirac Fermion. So that is a signature of topology, that it doesn't depend on chemistry, surface chemistry, dangling bond, or surface electronic structure, accidental. It's not accidental, it's intrinsic. It's a property of the Hilbert space of the system. So this is a very exotic object. So this is the state that is what was called topological insulator or 3D topological insulator, because it doesn't show any Hall effect. Okay. So now so that was kind of like a conceptual theoretical description. I did not go into the details of theory. It's a very broad audience. So now comes experiment. How do we prove that we have 4 invariant topological state of matter if we cannot probe these? So these invariants are like people who do symmetry-based phases of matter, like superconductivity, magnetism. Those states of matter are described by a order parameter, some order parameter. So if you know the order parameter exactly, you know the state. That is absolute characterization of the state as much as it goes. But in topological phases of matter, order parameter does not exist. It's not related to broken symmetry or symmetry, broken symmetry state. So they are described by topological invariance. So experimentally, what you have to measure is find a technique, find a way to measure this topological invariance and show that these invariants are basically invariants, that they don't change under deformation. So as I said, this 3D the topological state is described by 4 invariants, and you can call these invariants are like the quote unquote order parameter of the state. So there are multiple ways of measuring it theoretically, but the most successful one that can measure all 4 invariants is spin and angle resolved photoemission spectroscopy, and that is what we applied. You can apply. I hear some noise, background noise. Okay, anyway, so this technique the idea is to probe all the degrees of freedom of electrons on the surface and also on the bulk. So then you can do a bulk boundary correspondence, which is the essence of topology. And these invariants do not directly lead to quantized transport, unlike quantum Hall. So although doing transport would be interesting, but transport doesn't directly couple to topological invariant. That is the reason, in order to prove this state, we are doing spectroscopy. We are also doing transport, but I'll not describe transport because transport doesn't prove topology decisively. Okay, so the method itself is quite involved, and it took us a decade to fully figure out how to do this. I'm not going to describe the technical detail of the methodology, spectroscopic methodology that we have developed over or improved over the last 15 years or so. If you're interested, you can look up it in my group website. And I have listed the references because I'm not going to be talking about them. There is a review of modern physics article that I wrote with Charlie Kane in 2010. This review, about 2/3 of this review is about experimental paper. Very little theory is actually there. That is basically, these papers are kind of summarized in this RMP article. If you're interested in the details of spectroscopy, you're welcome to look at. Okay, so then I'll give the first example of topological quantum matter in 3D, as I said, described by 4 invariants. So this is the 3D topological insulator, or simply topological insulator. So here we are probing the bulk and the surface electronic structure with spin degrees of freedom. So what we see is that if we place the Fermi level inside the gap, we see there is a circular Fermi surface, which is on the surface, and this circular Fermi surface is spin texture, in other words, and in a time reversal invariant way. K plus, if K plus is minus, down, K minus is up, and it's for any diagonal cut across the Fermi surface. And there is a Dirac point that is protected by time reversal symmetry. And then the chirality reverses as you go above and below the Dirac point. This is momentum space chirality. And so how to interpret this in a physical way? So this means that an electron moving to the right, if it is spin down, then electron moving to the left is spin up, and that's all there is. So in other words, you have half the degrees of freedom. And if you take the generalized definition of Berry phase, then you have pi Berry phase, because you take electron on a closed loop. So then you have to rotate it 720 degrees to get 2 pi, right? So here you rotate it 360 degrees, so it's pi Berry phase, and the topological invariant is Berry phase divided by pi, so the strong invariant is 1. So this is the first invariant. Okay. So you can apply similar ideas to probe the surface and bulk and the edge to figure out this topological invariance, and so then the picture, simple picture that will emerge like this. So it's like in the bulk it's insulating, and on the surface you have all these helical Dirac Fermions that wrap the box. Okay, so why is this interesting and why is this unusual? It's unusual because now we see that K plus is all spin down, K minus is all spin up. So an electron trying to, now consider transport through a 1D channel of such a thing. Electron trying to take a, let's say this electron, which was moving to the left, it tries to take a U-turn and move to the right. So this U-turn is not allowed, because there is no available state, because it's spin up but here only spin down is allowed. So that means the backscattering is forbidden. So if you make a topological insulator where 1D channel, the backscattering is forbidden. We have also demonstrated that by doing STM scattering based on scanning tunneling microscopy. So this half Dirac gas is backscattering free. So why is this interesting? Because backscattering is the major dominant channel for resistivity for 1D, say a nanoware of topological insulator. So that means, so this would reduce resistivity quite a bit. Ideally, it will be almost non-dissipative. People have demonstrated that non-spectroscopically. We have done that spectroscopically. So this is interesting. You could, in principle, make topological insulator nanowares and reach low resistivity. So in some sense, you could compete with superconductivity at higher temperatures. Since this is not limited by superconducting TC, and we don't have any room temperature ambient superconductors. So this is our best bet for that. And we have demonstrated that this is possible at room temperature. For example, this helical Dirac Fermion backscattering free, it remains at high temperature. There may be inelastic backscattering at high temperature, but if your gap is large, if your topological insulator gap is large, then even at room temperature, in principle, you could perfect material that has not happened yet, that could compete with superconductivity in terms of transport applications. So this is very, very exciting because for the first time, topological physics existed with the quantum Hall. As I said, a few Nobel Prizes have been given for quantum Hall effect, which is topological, but all of that at very low temperature, millikelvin. But a dramatic advancement is that this topology is now at room temperature. So this opens up future possibility for exciting applications. And US DARPA is investing, and also DOE is investing quite a bit on improving this. So the discovery of these topological properties led to many other new developments in condensed matter physics. I'm not going to describe them. Many groups worldwide are working on it. So this slide is quite old. It's actually a 10-year-old slide when there was already 500 experiments that followed up on our work. This is 10-year-old slide, and now it should probably 5,000. Okay, so where to go beyond that? What do we do with a topological insulator? As I said, there are two directions. One is fundamental physics, fundamental condensed matter physics. The other is kind of develop application. I work on fundamental physics. I'm not trying to find application of these things. So what I'm interested in, or I have been interested in since in last 10 years, is starting with a Dirac Fermion. This consider QFT, quantum field theory, half fermions. Can we realize half fermions? So one such half fermion would be if you split a Dirac Fermion, it can only split into Weyl. They're chiral, they're like monopole in momentum space monopole and anti-monopole. If you split, the only way to split a Dirac Fermion is you can get a pair of Weyl fermion. The other way is if you induce superconductivity. So one way to create a Weyl fermion is to break symmetry, time reversal symmetry. So then you get, you remove the degeneracy, so you create Weyl. And here so you could do that with magnetism. And then with superconductivity, you could create Majorana fermion. Those are also half fermion. So their wave function is real. So if you have real wave function, then particle would be its own antiparticle, because if you take complex conjugate, a real number gives you real number. So this is why Majorana fermion is its own antifermion or antiparticle. So starting with Dirac Fermion, we now want to create more fundamental emergent fermions like Huff fermions, Weyl and Majorana. I'm not going to go into details of those things. We have papers on that where case for Weyl is clear, Majorana remains unclear. There is more work to be done. So I'm now going to move into a different thing. I'm trying to show that how other emergent phenomena, strong correlation can be brought into the picture, into the topological physics. Before topological wave, condensed matter was more dominated by strong correlation, many body physics. So I'm going to move into that direction. We have been also working on that. So the story is intertwined. So as I said, you start with a topological insulator, introducing superconductivity. You can create Majorana Huff fermion, or you can create by introducing magnetism, you can create Weyl Huff fermion. Those are natural things. So those are quantum field theory objects. Okay, so as I said, so I described topological insulator and then said that what it can do. Now I'm going to move to the next topic. How about topological magnets? Do you have topological magnets? So that is how we are merging strong correlation physics and quantum topology. So so in this case, I will combine not only just spectroscopic, also transport signature to create a sense of Berry curvature field and quantum geometry. So as I said, topological insulator is the starting point. We start with a topological insulator. We can magnetically dope it in the bulk or on the surface. In this case, we were doing that back in 2010 on the surface, and we create a gap. Now, how do we know that this gap is a topological gap? It's not a trivial gap, meaning that this gap is a Chern gap, not just a band gap. So it took a decade to actually develop the spectroscopic method and technology and ideas to prove that this gap is a topological gap, meaning it's a Chern gap. So I'll tell a little bit about that. So one thing we do is we probe the surface circular dichroism, come in with right and left circularly polarized light and see what is the difference, and look at magnetization, whether there is hysteresis, and whether this hysteristic behavior is correlated with the gap. And then if we raise temperature, this signal should disappear if it is correlated with magnetism, because as you raise temperature, if it is interaction phenomena, then it should above transition at some point, it will disappear. So more decisive check, as we discovered through experiments, is to do a spin texture of the gap. So if the gap is trivial, then there would not be any spin texture. The spin texture would also be trivial. For example, this is trivial gap, there is no spin texture. When there is a non-trivial gap, there is a spin texture. In other words, the spin texture at the edge of the gap in energy momentum space is hedgehog-like. So this hedgehog is a signature of topology, that something in momentum space is twisted in some way. So there is a twist introduced by magnetism in its wave function space. So then we can also look at the Berry phase tunability by gating on the surface and see how, whether there is Berry phase tunability. That means clearly it's Berry phase or Berry curvature field that is creating the topological twist. So this is the signature, that if you have a topological gap, then it will be hedgehog-like. If it is trivial gap, it will be like that. And so then we, armed with this set of ideas, then we started to probe Kagome magnets, because Kagome magnets have Dirac Fermions and also flat band. Flat band is a good test bed for strong correlation. For example, in twisted bilayer graphene, by twisting, you create a flat band. So then your bandwidth competes with interaction scale, so you could get strongly correlated phenomena. So the Kagome magnets are interesting because, unlike twisted bilayer graphene, you have not only you have flat band, you also have Dirac Fermion, which you can twist further to create topology. And it's a spin orbit system. In twisted bilayer graphene or graphene systems, spin orbit is very weak. So in my view, this Kagome magnets with spin orbit are far more interesting than twisted bilayer graphene, although we haven't found superconductivity yet, but the search is on. You never know when that will appear. I think there will be more surprise in spin orbit Kagome magnets than bilayer graphene. Okay, so as I said, that if you have a Dirac Fermion in Kagome magnet, then if it is magnetized, there is out of plane component, you can create a Chern gap, meaning that band gap is topological. And this is what we demonstrated first in 2012. That was the method that how do you know that your gap is a Berry curvature field twist. And then more recently in this Nature paper, where we showed that is true for Kagome magnets. Okay, so for the Kagome magnet, since it's 2D, it's STM works better. I have a funded STM groups. I operate 3 STMs in my Princeton lab. So it's this data is taken with one of my STMs. So here, first with STM, you want to say whether you have a Kagome lattice or not, right? So that once you know you have a Kagome lattice on the cleaved plane, then you can apply a field to look at either look at the Landau level or look at the anisotropy. If you have nematic order, then that's clear sign of strong correlation. For example, in this iron compound, we clearly see, even though the crystal structure, the surface is, it has a hexagonal structure, electronic structure is twofold. So clearly there is nematicity. Not only that, of course, there are many systems are nematic, nematically ordered, but what is new or unprecedented in this compound, in all of condensed matter physics, is that here using a magnetic field, you can dial the nematic order direction. So that I don't know of any other system that can do that. So in other words, you have control over nematicity. And then you can, when you apply a field out of plane, you recover the crystal symmetry, the 6-fold. So the electronic structure is now 6-fold. So strong correlation has driven this system, this Kagome magnet, into a nematically ordered system. So we have more detailed exploration of the system. So far, let me summarize. Back in 2012, we observed magnetism and Chern gap in a topological insulator, but we could not observe the edge state. As I said, topology is about bulk boundary. It was not accessible to experiments, and Landau levels were also not resolved in transport or spectroscopy. In 2013, a year later, a group in China, Chikun Shui group, Tsinghua-based group, they observed quantum anomalous Hall state, which is a signature of the edge state at millikelvin temperature, or at least sub-Kelvin temperature, in chromium-doped bismuth-based topological insulators. But this, they could not do any of that stuff. They cannot isolate edge state or do edge state spectroscopy. Then another next development in 2018, where we showed that you can probe both the Chern gap and through spin QPI using STM can observe magnetism. And anomalous Hall effect was seen in transport by a group at MIT, but again, edge states were not accessible to experiment. So what is the outstanding problem in the field is that this was the goal in 2008, identify or make a 2D Chern magnet in the quantum limit where edge states are accessible, Landau levels are accessible, and Chern gap is large, more than 25 millivolts. And in the interacting limit, there might also be some many-body physics. One example would be Kondo lattice physics. So this was the goal in 2018. And then around 2019, we finally discovered a compound where it meets all these requirements. So this compound has a topological gap larger than 25 millivolts. So it's in principle room temperature operable, and it has edge state accessibility. And not only that, you can tune at the rare earth site to do variant magnetism. So it turns out that the terbium part is ideal because it's out of plane. So the Dirac Fermions are fully gapped by the magnetism. In these other cases, it's partial. Okay, so it turns out our collaborators have succeeded in making very clean Kagome lattice compared to other Kagome lattices we have studied with our STM. You can see that compare this new compound is within this patch. There is no single defect. There is defect elsewhere, but you can find patches as large as these with nodes. So this is really now a model system or ideal Hamiltonian system that you can probe. So this paper appeared in Nature last year. So now you apply a magnetic field, you can clearly see the distinct Landau levels, and only on the surface, on the Kagome surface, not on other surface, because the sample can cleave in other surfaces. And then when you probe the details of the Landau quantization and try to fit, then you see that it has a Dirac, massive Dirac Fermion fit, meaning that this has a Chern gap type fit. And the Fermi level is 130 millivolt away from the Dirac point, and it's pinned here, and it's nonlinear. So high Landau levels being nonlinear it's a classic signature of Dirac physics. If you follow graphene literature, you may see that the graphene paper showed such a thing. So now we are finding that in a Kagome magnet. So this is very, very interesting. So now it's consistent with our theoretical calculation that the gap has spin orbit contribution. That's something not there in graphene. As I said, we want spin orbit for topology. It's much rich, it gives you much richer physics. So now if, as I said, that, okay, so we have seen Chern gap before Landau quantization before, but then how about the chiral edge state? Can we find the chiral edge state? So this chiral edge state would be kind of like, it will have Luttinger liquid behavior. So now with STM spectroscopy, as we scan the edge, the step edge, we see that only when we bias 130 millivolt, meaning that when this number we get from the fit, only there it lights up. So in other words, the edge state is, there's a robust edge state inside the gap. And also with spectroscopy, we see that this edge state is backscattering free, meaning this is chiral edge state associated with Chern number 1. So this is topological. So now we have the bulk boundary correspondence. The sample is not exactly in the quantum limit, so our sample growers have been putting in effort to dope or undope the system to the quantum limit, so it's would be more exciting. And the numbers we get from spectroscopy STM, they are consistent with the transport results. As you fit the transport results, you get same parameters. So this is a very clear signature, very clear demonstration of a Chern magnet. This is Chern number 1. Okay, so now that we know how to probe Chern gap, Chern magnet, all these things, we can also try to find Weyl magnet in the same line. But this idea is not new experimentally. Experimentally, we were talking about this idea back in 2010, 12, 11. You can find those ideas in our paper, like Suyang Zhu's science paper 2011, when we are probing topological phase transition. At the critical point, we have a 3D Dirac. So I asked my student, who is now a professor at NYU, to magnetize the Dirac critical point. Then the only way to split Dirac fermion is to split into a pair of Weyl fermions. And I asked my other students, Madhav Newpen and Shankar, to magnetize the bismuth antimony compounds and cadmium arsenide analog. Madhav is now a professor in University of Florida. And then I asked Suyang to search in the database to find I-broken, inversion broken materials that are analogs of this idea. Suyang is now a professor at Harvard. Okay, so based on those ideas, we came up with a theoretical algorithm how to find Weyl or magnetic Weyl. You start with a topological insulator, drive it to a critical point, just as we did in the previous slide, and then break symmetry. So then you will get, Dirac will split into a pair of Weyl, and the Fermi surface, circular Fermi surface, will split into a pair of Fermi arcs, disjoint Fermi surface. This is very, very strange. That has never been seen before. So the algorithm for doing that, finding magnetic Weyl or those things, came from our topological insulator and topological quantum phase transition ideas. And these three students have played critical role in the discovery, conceptually discovered this thing. Okay, so then here again, you have to track the chiral edge mode, do chiral edge modes co-propagate. And with spectroscopy, this loop cut, we could show that there's a pair of chiral edge mode, they co-propagate. This is very strange case, because if chiral edge modes co-propagate, then their projection, well,
Professor Zahid Hasan,
yeah,
your time is nearly over. Just can you?
Yeah, I'm also getting close to my talk. So then these Weyl nodes, when you project on the surface, they are connecting the arc. So the Fermi arc is kind of like a Dirac string, and the Weyl node is like Dirac monopole. So then the Dirac string should originate from monopole or anti-monopole, and that is what we see. And that is our proof, topological proof of Weylness. So since my time is almost up, so I will just take 1 minute to wrap up. So then we predicted a 3D topological magnet. This is a theory paper led by my theory postdoc, Guoqing Zhang. We predicted where you could find a topological magnet that has the new type of edge modes, like drumhead, continuum of edge states. So I'll not go over the details and go to the summary. That now, if you take the topological state and then use ARPES data to as input to DFT, you can calculate the quantum geometry. And if you know the quantum geometry based on experiments, then you can predict transport. For example, we predicted anomalous Hall transport of this topological magnet. We said that this anomalous Hall transport would be around 1,000 standard units. And indeed, when our collaborators measure transport, it's 870. So in other words, our spectroscopic methodology has now matured at a level that we can predict transport. So this is my concluding slide, that with with the discovery of topological insulator, we have taken it into many directions, introduced superconductivity, magnetism. I mostly talked about magnetism here, and strong correlation like nematic Kagome magnet, drumhead states. And then we showed that spectroscopy and transport correspondence. In other words, starting with spectroscopy, I can predict transport before measuring and then get the numbers right. So the topological magnets work that I presented, you can find, I did not go over all the details. I sort of gave a high-level summary type of talk. There's a very broad audience. You can find the technical details in this paper. If you are interested in even more deeper technical details, I wrote some half-dozen reviews starting the RMP in 2010. You can find far more technical details in these review articles. With all of that, just one sentence that where is the field going? Topological insulator Dirac Fermion, split it, get a half fermion, get to Majorana or Weyl, and then you can make qubit out of these things. These qubits are fault tolerant. I just got funded by DOE about more than $1 million to make qubit out of this type of thing. So DOE is very excited about our work. DOE is US Department of Energy to take the field to develop next generation quantum computing. So that's the application part of it. Thank you.
Thank you. Thank you, Professor Zahid Hasan, for an wonderful talk that we have had. We do not have time. We're running short of time. Therefore, I would like not to take any questions now. Kindly, those who have any questions, can you write them in your chat box so that we can send it to Professor Zahid Hasan later. Now we move on to the next talk of this plenary lecture session. Professor Khandakar Abdul Muttalib is going to speak now. Professor